In this last video on vertical circular motion, I want to look at the case where the particle can leave the vertical circular path, but it can leave it now from the outside rather than in the previous video leaving it on the inside. So the situation here might be something, as I've mentioned here, like a particle rolling down the outside of some kind of ball, sphere, cylinder, something like that. So this is a little different from the other cases, because in all the other cases I've assumed that we're starting at the bottom of the circle. In this case I want to look at a situation where it starts at the top of the circle. So starting it with some speed u at the top here, and it's going to roll around the outside of the circle, and we're interested in the situation at some point around its path when it's travelled through an angle theta, now measuring that angle theta from the upwards vertical rather than the downwards vertical. So as with all of the vertical circular motion cases, we can deal with this as a change of energy to begin with. Notice now that what we've got is a normal reaction force, so perpendicular to the surface, because the object is, and the particle is on the outside surface. We've got a normal reaction pointing out away from the centre of the circle. So that's a thing to notice about that, but we'll look at the forces in a moment. Let's just do the energy thing. So here we're going to be gaining kinetic energy. Okay, gained. And we're going to be losing potential energy, gravitational potential energy, as the object of the particle loses height. So Ke gained is going to be equal to gravitational potential energy lost. So expression for the kinetic energy gained is going to be half mv squared minus a half mu squared. Sorry about my m's, they're not very well written, but there we are, I'm sure you can manage. Gravitational potential energy lost is going to be mgh, and it will only take you a moment of thought to see that actually the h, the change in height here, is going to be the same expression that we've had when we were starting from the bottom of the circle. It's just r brackets 1 minus cos theta, so we can use that kind of approach again here. And we've got m's cancelling out through this equation as well, as we always seem to have, multiplying by 2 perhaps to make things a little neater, gives us v squared minus u squared equals 2g, and then we've got r brackets 1 minus cos theta for our change in height. So exactly the same sort of approach that we've had before, and exactly the same kind of expression. Now that's the most general case, and then as before we can, once we've got an expression for v squared by sticking u squared on the other side of that equation, then we can use that in our radial acceleration, looking at resolving the forces along the line of the radius and putting that equal to mv squared over r with an expression for v squared that we can establish. I want to look at this in a particular sort of situation where we start by just nudging the ball from the top of the circle, so essentially taking u to equal 0. So if u equals 0, then this equation just becomes v squared equals 2gr1 minus cos theta. And it will only take you a moment's thought to realise that actually what's going to happen in reality here is that this particle is going to roll around the outside edge, and at some point it's going to leave that circle and carry on as free motion under gravity, the kind of projectile type of motion. But we need to work out where this is going to happen. Where is this particle going to leave that circular path? And so, as before, when the particle was leaving on the inside of a circle. We had the tension in the string equaling 0, essentially the string going floppy. Of course, on that previous case, it needn't necessarily be on a string. It could be on the inside of some sort of circular thing, like this one is on the outside in this case. But on the inside, it might where the equivalent of the tension in the string being equal to 0 would be the normal reaction from the surface that it's rolling around would be equal to 0. And the same is true here. Just because the reaction is pointing outwards away from it, essentially what's going to happen here is the particle is going to lose contact with the surface that it's rolling on, and when it loses contact, that R becomes 0. And so we can look at the case. Let's have a look at a general case including the R to begin with. So if we just look at F equals ma radially, as we did in the previous video, then our forces, our radial forces here. So we've got the reaction force along the line of the radius, so that doesn't need to be resolved, but it is away from the centre, so that's going to be a minus R in this equation. The positive force is going to be a component of that mg, and it shouldn't take you a moment of thought to recognise that what we've got here is that this theta with the upwards vertical here is now repeated inside this right angle triangle in this little corner here. So let me just mark that angle in there. So that angle there is theta, the same as the one at the centre of the circle. And for the radial component, there we want the adjacent side of this right angle triangle we're splitting our weight up into. And so we need the cos theta component to be the radial thing. So we're going to have mg cos theta going directed towards the centre of the circle, and we've got R directed away from the centre of the circle, and that gives us our resultant force in our F equals ma equation here to be mg cos theta minus the normal reaction. So that's our F. And then mv squared over r gives us m, and again we can just use this for v squared, so we'll have m over r, and then v squared being 2gr 1 minus cos theta. And we can see that the radius of the circle is going to cancel out here. So we've got mg cos theta minus r equals 2mg brackets 1 minus cos theta. So we're interested in finding out where the particle leaves this circular path. So that's going to happen, I said, when the normal reaction is equal to 0. So it leaves circle when R equals 0, and so we can just remove R from this equation that we've got here to leave us with mg cos theta being, oops, sorry, that's not very clear, equals, we can work that one out, equals 2mg brackets 1 minus cos theta. Equals a little bit clearer, actually, because I'll confuse myself thinking it's a minus otherwise. So we've got mg cos theta equals 2mg 1 minus cos theta, and let's have a look at this. The m's cancel out in here. So you'll notice here that we've got a situation where both the radius of the circle and also the mass of the particle cancel out through this equation, and therefore this situation, the leaving of the outside of the circle here, must be independent of both mass and radius. So let's just tidy that up a little bit. What we've got here is we've got g cos theta on the left, and if we expand that bracket on the right hand side of the equation, we've got 2g minus 2g cos theta. So we've got a g cos theta on the left and a minus 2g cos theta on the right. Those two terms can be combined with each other to leave us with something. Oh, and the g's cancel out, incidentally. I could have done that a line earlier, couldn't I? I didn't spot that one. So we're left with a situation where we've got cos theta equals 2 minus 2 cos theta. So this now just has theta as its variable, and that means we can solve it. So 3 cos theta equals 2, and cos theta equals 2/3. And if we just work out the inverse cos of 2/3, that gives us theta being an angle of 48.2 degrees. And so remember that this is dependent on the fact that we started with no speed at the top of the circle. So this result will change. The result we've just established there will change if you give it some speed at the top of the circle. We'll end up with a different angle. But in that kind of situation, regardless of the size of the circle or the mass of the object, it will always leave the contact with the surface on the outside there at an angle of 48.2 degrees.